Hey, here's another screencast giving an optimization example. I call it inscribed parallelogram. Here's the problem statement. Find the area of the largest rectangle that can be inscribed in a semicircle of radius 10. So the way we do this, first, so you understand what it means to be inscribed, what we're going to do is we've got a semicircle, and a rectangle is inscribed if its vertices are on the semicircle. So here's an example of an inscribed rectangle. Another example of an inscribed rectangle would look like this. And notice that the rectangles have to be symmetric inside the circle for their vertices to lie on the circle, or in this case on the semicircle. Here's another inscribed rectangle. So you get the idea. I'll draw one more. You could get a really low and wide semicircle down here, or a rectangle. So those are examples of inscribed rectangles. I want to find the inscribed rectangle that has the greatest area. So you can look at this red rectangle here and see that it's got a small area because it's really short, even though it's wide. And the green area here, this also has a small area because it's really narrow, but it's tall. So somewhere around where the blue and the orange rectangle are is the rectangle that has the largest area. And we want to find what are the what's the area of the largest rectangle that's inscribed. So this is an optimization problem because you see this superlative largest. And what is it that we're optimizing? Well, we want to find the area of the largest rectangle. So the function we're optimizing is an area function, the area of some rectangle. And we know the area of a rectangle is its length times its width. And generally, when you're talking about a rectangle, you can make a rectangle of any size, any length, any width. That would give us, in this problem, two variables. But in Calc 1, we only know how to optimize functions of one variable. So we need to get rid of one of these variables. And so we're going to take advantage of the constraint that we're inscribing our rectangle to get rid of one of these variables. And let's see how that works. So I'm going to draw a semicircle of radius 10. The way I'm going to do that is I'm going to put it on coordinate axes. So the center of the circle is going to be at 0, 0. And I know a circle of radius 10 has equation x squared plus y squared equals 10 squared. So this point over here is going to have the coordinates 10, 0. This point up here is going to have the coordinates 0, 10. And the semicircle itself, this arc, it's going to be described by the function, where should I write it? Down here, y equals the square root of 10 squared minus x squared. You just take this equation and solve it for y. So this is the graph of my semicircle. And when I inscribe a rectangle on the semicircle, it looks like this. Let's use this fact to figure out how length and width are related to one another. So let's say, I'll do this in green. Let's say that this distance here is A. What is this distance? Call it B. Well, if this horizontal distance here is a, I can use this function y to tell me that b, which is the height of my rectangle, it's the height of my semicircle when I go a units away from the origin. So b is 10 squared, or the square root of 10 squared minus a squared. So that gives me a relationship between a and b. So with that in mind, is that if I say, so let's go back down to the left side of the page. If I say b is the width of my rectangle, and I'm going to say I want to use a as my length, but really it's 2a. 2a is my length. Then b is 10 squared minus a squared. The square root of 10 squared minus a squared. So what does that tell me that the area of my rectangle is? Well, area is length times width. Length, I said, is 2a. Width is the square root of 10 squared minus a squared. So there we go. There's the formula for the area of my rectangle. And let's call that a of little a is 2a times the square root of 10 squared minus a squared. And here, a is really like the half length, looking at my picture. So we want to maximize this. We know from calculus that maxima occur at critical points, and critical points have three flavors: endpoints, singular points, and stationary points. So what are our critical points in this case? Well, let's look at endpoints. You can look at this function, and you can see there's something interesting happening here. Let's copy this over to the next page. So we can ask the question about the domain. The domain of this function, this domain of this area function. And if we look at this from an algebraic perspective, the domain of this function is a symbolic function here. Really depends upon what the sign of this is. We don't want the thing under the radical to be a negative number. So we need to constrain 10 squared minus a squared to be greater than or equal to 0. So that's saying 100 is greater than or equal to a squared. So there's a bunch of ways you can solve this. The most efficient way to solve it would be to look at the first inequality there. Well, and write it as a difference of two squares. And you want this difference to be greater than or equal to 0. And that leads you to create a chart of signs. And we're going to put where the left-hand side is 0. And so the left-hand side is 0 at negative 10 and 10. And let's write down the two factors. And then we can put in the signs. So the first factor, 10 minus a, on these three subintervals, it is going to be positive, positive, negative. And 10 plus a, on these two intervals, it's going to be negative, positive, positive. So 10 squared minus a squared, when you multiply these two things together, it's going to be negative, positive, negative. So this tells us the leftmost interval is bad for my area function. The rightmost interval is bad, but the center interval is what we want. So our domain, this is the place where our 10 squared minus a squared is greater than or equal to 0. So this is the algebraic domain. Of my area function. It's the set of a values between minus 10 and 10. But let me draw your attention to the context from which this area function arose. I'm going to go back. It was here. We built this area function from this idea of length times width, and we looked at this a and the b to help us build the length and the width. So here's where a is in the picture. A is the length of the rectangle as it extends into the first quadrant. So the smallest a can be really is 0. And indeed, the biggest a can be is 10. So the contextual domain of a is really the interval from 0 to 10. And this is important to us because it tells us that the endpoints are a equals 0 and 10, not negative 10 and 10. So let's look for the next critical points, the singular points and the stationary points. Before doing that, let's take the derivative of our area function. So it's right here. We have to do the product rule. So we get 2 times the square root of 10 squared minus a squared plus 2a times the derivative of the square root function. Sorry, I didn't plan that spacing very well. Let's recopy here. And let's look to see if there's any cancellation. I've got a 1/2 in here with a 2 in the denominator. I'm going to let that 2 cancel with that 2. And then notice over here there's a minus 2a. So that minus sign is going to come out and change that to a minus sign. And this 2a will combine with that a to give me a 2a squared. And then that negative 1/2 will put that expression in the denominator. So let's look at this. Think about stationary points and singular points. So for the stationary point, we're going to take this and we're going to set it equal to 0 and try to solve for a. We'll do that in a second. For the singular point, we're interested in where the derivative doesn't exist. And notice, you look here, always your attention should be attracted to the denominator when you're asking about where functions don't exist. And so where does this denominator vanish? Is there any way where that it vanishes? Well, it vanishes where the thing inside the square root vanishes. And that is precisely when a is 10. So there is a singular point you can see. It coincides with an endpoint, which is interesting. It's not adding an additional critical point to our consideration. So let's turn our attention to stationary points. So we want to solve a prime of a equals 0. So we're going to put a 0 right here. And what I want to do, I guess, is I want to take this difference, I want to write it as a single expression. So I'm going to take the first term and I'm going to multiply it by the denominator of the second term over the denominator of the second term. So I'm going to get a common denominator. Now let me just recopy the second term here. So you'll see by doing this, though I get a common denominator, which is good. Let's write that. And the minus 2a squared comes from the second term. What's happening in the first term? Well, what I just multiplied by is the same thing as was in the first term. So what I get is 2 times 10 minus a squared. That's it. Oops, almost missed this. All right, so what do we do next? Let's copy it. Oops, let's copy this to the next page. So we're solving this. And so we get 2 times 10 squared minus 2a squared minus 2a squared over all this. Simplifies to 2 times 10 squared minus 4a squared. Now we can multiply both sides by the denominator. That is, we can clear the denominator, and so that gives us 2 times 10 squared minus 4a squared. And now we could divide both sides by 2. And so that gets rid of that. And then this 4 becomes 2. And that gives us a squared equals 10 squared over 2. So a, taking the square root of both sides, is plus or minus 10 over root 2. But a always has to be positive. So we get a equals 10 over root 2. All right, so that's our stationary point. Now we can go use calculus and the first derivative test for local extrema to determine or to show that this is actually a maxima of the area function. So here's my number line for my chart of sines. I'm going to put our endpoints, 0 and 10. And I'm going to put my critical point here, 10 over root 2. And let's make a chart of sines. So I'm going to put over on the left-hand side my derivative. So where's my derivative function? I was just working with that. Yeah, that's right. Let's see. I guess this is the derivative function. But I came down here and I did a bunch of work and simplified it. So I'm simplifying it here. I'm getting this right here. So if we look at this, we see the denominator is always positive. So the sign really is up here. And I can move the sign right here. And we got this. And so I can really just work with this. This here, if I factor this recognize this as a difference of two squares, I get 10 minus square root of 2a times 10 plus the square root of 2a. So I can put these as factors here. And the sign of these two factors will determine the sign of my area function. So let's fill out the chart with this. Looking at the second factor, you can see it's always going to be positive because a is always positive, and so you're adding two positive numbers. The second function, it changes signs. When a is really big, 10 minus square root of 2 times a is going to be negative. So here we could plug in, I guess that would be good for us to know this. 10 divided by the square root of 2 is approximately equal to 7.07. So if I plugged 8 into the first factor, I get 10 minus 8 times the square root of 2. And let's just 8 times the square root of 2 is 11.3. So the first term is negative. So there would be a negative here. And we can go and say plug in 1 and we see that's a positive. So looking at the signs of these two factors, we see the derivative itself is positive on the first interval and negative on the second interval. So the first derivative test tells us that indeed that the critical point a equals 10 over root 2 is a maximum. But the problem asked us to find the area of the largest rectangle, so let's do that. This rectangle has area A of 10 over root 2. And our area function was 2 times a times the square root of 10 squared minus a squared. So let's work this out. That's 20 over root 2, or if you like, 10 times root 2, times 10 squared minus 10 squared over 2, and 10 squared over 2, that 100 over 2, that's 50. So we get 10 times root 2 times root 50, which is 10 times the square root of 100, which is 100. So the area of our largest rectangle is 100. Pretty cool. The square of our radius. Problem done. Thanks for watching.